Okay, so let's learn about cosine today. The good news is that everything that we talked about yesterday, the A, the B, the C, the D, they're all exactly the same. All right, so how they affect the curve, exactly the same. Now, what is different? So let's look at this unit circle. I know it copied like super teeny tiny on your page, but here's what matters. If we are going to graph cosine, all that really matters are the values of the x coordinate. So let's look at those as we go around the circle. If we start at 0, the x coordinate is 1. Then it goes down to root 3 over 2, right? Because the distance from here to here, this distance was not a full radius. It was less than 1. All right, then it gets less, then it gets less, then it's a 0. Then it goes negative, bigger negative, negative 1. Then it's still negative, but smaller negative, smaller negative, smaller negative, 0. Then 1/2, bigger positive number, back to a 1. Okay, now the sign values are exactly the same. Like the numbers I just circled, if you look at the y values of the ordered pairs, they're the exact same numbers, just in a different order. So let's think about the sine curve, since we talked about that yesterday. The sine curve starts at 0, goes to its max, goes back to 0, goes to its min, and then goes back to 0. So that's its order. The cosine curve starts at its max. So it starts at its max, it decreases to 0, it decreases even more to its min, then it starts increasing back to 0 and increasing back to its max. So it has kind of like a different order to it. So let's look at it. If we just fill in our t-table here, our cosine value at 0 was 1. Our cosine value at pi over 2 was 0. At pi, it was negative 1. At 3 pi over 2, it was 0. And at 2 pi, it's back at 1. So if we plot those points in that particular order, right, those are the same points we were plotting with sine, but they're in a slightly different order. This starts at the max, goes through 0, goes to the min, goes back through 0, and ends back at the maximum. So, remember that I said that the sine curve had one hill and one valley? The cosine curve has a full valley, and it has half of a hill over here and the other half over here. The cosine curve is literally the same curve as the sine curve. It's just snapshotted at a different position. So if we look back up at this that I pointed out to you yesterday, if we started right here, or no, let's start right here. We go up, then we come down, and then we come back to 0. There's your sine curve. Okay, if you start here, you can get your whole sine curve. If you want your cosine curve, you're going to start right here, and here are your values for your cosine curve. It's literally the same curve. We're just snapshotting it in a different place. What I want you to be thinking about is the fact that we oscillate between a maximum and a minimum. So let me give you an example. Does everybody know how the moon cycle works? Right? It goes from full moon, it decreases to a new moon, which is the moon you don't see, and then it increases back up to a full moon, and then it repeats itself. And it goes on forever and ever and ever. Well, that would be considered sinusoidal. If we were going to track that on an XY axis, and we were going to put maybe fullness of the moon on the y-axis and time on the x-axis, it could look like a cosine curve if what we were tracking it was from full moon to the next full moon. And that would take about 28 days. All right, full moon, half moon, no moon, back to half moon, back to full moon. Now, if we wanted to track it from half moon to half moon, that would be a sine curve. So if we wanted to track it from half moon up to full moon, back to half moon, down to no moon, back to half moon, then we would call it a sine curve. So the thing is, they're the exact same curve. It just depends on what are we using it for. And so sometimes, depending on what we're using it for, we will use it as a cosine curve, and sometimes we'll use it as a sine curve. When we're graphing, like I said, everything is going to be exactly the same. So this would have an amplitude of 2, but it did get flipped. So we're going to go up to 2, we're going to go down to 2. My tick marks are still going to be the same. Pi over 2, pi, 3 pi over 2, and 2 pi. But it starts high, goes through 0, goes low. Oh, wait, is it going to start high? Ah, because this got flipped. So we're actually going to not start up at the top. We are going to start down here, go to 0, go to the max, come back to 0, and go to the min. So this one will look like that. For this one, the only thing that's changed is that we have gone down 3. So we will draw in our midline. 1, 2, 3, 4. I'm going to draw in my midline right here. My tick marks are all going to be exactly the same. So pi over 2, pi, 3 pi over 2, and 2 pi. And then the amplitude is still a 1. So I'm just going to go up 1 and down 1, from my midline. So I will start here, back to the axis here, down to the minimum, back to the axis, and up to the maximum again. All right, so any questions on the graphing before we move on? Okay. So we saw these kinds of questions yesterday, and I think now that you know that they come from the same curve, they might be a little bit more challenging because you might be looking at this and thinking of a sine curve when you actually maybe should look at it and think of a cosine curve. Okay, so just be aware of that. Let's see, it does look like it went up, so I'm going to mark the midline right here at y equals 2. My amplitude was just a 1. Now the period length, okay, I need to highlight it so that I can see kind of where it starts and where it ends. Now remember, I'm looking for cosine here. So it could start here, it could go to its low point and then back to its high point. And by doing that, I can see it did start at 0 and end at 2 pi. So the period is 2 pi, so it is unchanged. And so I believe that we could get this equation as cosine of theta plus 2. But, yeah.
On the test, can you say like x or theta? Like, does it matter?
It doesn't really matter. We tend to use theta, the Greek letter theta, anytime we're talking about angles, but it really doesn't matter. I did want to point out to you, let's look for a sine curve here. So let's see. I see a full sine curve. If I start here, and I go up, and I come back down, and I come back to the midline. So I could technically also give an equation for this exact same curve using sine. It will be a completely different equation than the cosine one. This equation would be, let's see here, y equals, the amplitude's still a 1, sine, it did shift in this case pi over 2 to the left, so theta plus pi over 2, and it still moved up 2. If you were to type this into your graphing calculator in y1, and you were to type this into your calculator for y2, they would graph the exact same curve. So I think, you know, for this whole worksheet, it'll all be cosines that you're looking for. On the quiz, it'll kind of be open for your interpretation. And I usually on the quiz, if this was the picture, I would probably have both of these answers kind of ready to go on my key, depending on, you know, which one you highlighted and which one you did. Okay. All right. So what do you see that's changed here? Mallory? Is it tighter? Okay. So how would we figure that out? Let's find max to min back to max. Does it fit? What space does it fit in? It still fits in 2 pi. So this does still fit in 2 pi. So what else? Let's see. So the period is still a 2 pi. Here's my midline. So that's definitely changed. What else? It looks like my amplitude has changed. So this equation would be y is equal to 2 cos of theta minus 1. Please do feel free to use a highlighter to be able to kind of see, you know, or just, you know, scribble it over with a colored pen or a pencil. Ooh, this one's definitely, something's weird going on with this one. And it can be deceiving if you just look at the shape, because the shape may look the same. You have to look at the axes. This one is starting here, going down, and ending here. So it is actually, it got stretched. It got stretched by a factor of what? By a factor of 2. So I'm going to show you the shortcut way to write this equation. I can tell that it got stretched by a factor of 2. So I'm actually going to divide by 2. So I know that in my equation it's going to be theta divided by 2. Now, if you're like, whoa, wait, how would you know that? Here's how I would know that. I would look at this and I would go, okay, my period is 4 pi. Now we go to our equation and we'd say, all right, well, if the period is 4 pi, I have an equation that says period is 2 pi over b. Okay, well, I know that p is 4 pi, so I'm going to replace this with a 4 pi. So 4 pi is 2 pi divided by b. Well, wouldn't that make b a 1/2? Because 2 pi divided by a half would make it 4 pi. So that's how I would know that this is a 1/2. The equation process will work 100% of the time. Okay, so just look at your axis, figure out your period length. You can always use your equation to find your b value. But it can be done faster than that. If you look at it and you go, oh, did it stretch or shrink? And by what factor? And then remember, it's the opposite operation. Let's finish this one. This one went up 2. And its amplitude is still a 1. So there we go. Any questions on that whole B stuff? Yeah.
How did you know? So like, say if it like wasn't 4 years, like 3 years, something like that. How did you know how much it like stretched?
All right. So you're always going to start by just looking like how much space did it happen in. So your example, let's say this curve happened in a space of 3 pi. That one might be a little bit harder to do without the formula, because it's not like a perfect multiple of 2. So in that case, what I would do is I would use, okay, the period length is 2 pi divided by b. This is the period length. So then I would do 3 pi equals 2 pi divided by b, and then just cross multiply to solve for b. Yeah, so that's a really good question because that will come up. But if you can tell that it's just a multiple of 2 pi, there's usually a pretty shortcut to doing that. All right, this one, ooh, what if you look at this one and you go, oh, here's where it starts, and then you try to write the equation with that. What problem will you have if that's what you highlight? Fenton, do you see a problem here?
You only have half this cosine curve.
Yeah, I don't know where it ends. So how am I going to figure out how much space it took? So just be careful with that. Make sure that you can see a full curve. Yeah.
Can you just like flip it?
Yeah. You mean like that?
Like there's a full curve.
Yes. So if you flip it like that and then you realize, oh wait, what if I didn't start it there and instead I started it here? Yes. That's what we want you to see. But it may take a little bit for you to see it upside down. So do look for them upside down. This one's obviously been flipped. It's been moved up 2, and the amplitude is a 1. So this would be y is equal to negative cos of theta up 2. And the space was still 2 pi. So I knew that there was no change to the theta. All right, this one looks like, see, I looked at this one and saw a sine curve right away. Right, because it starts at the origin. So let's see, I think this one you kind of have to start this one maybe here. So this is a flipped cosine with an amplitude change and a movement left. Anybody want to give a shot at the equation? Well, normally it would start like on the origin, so it definitely went left, but it would be a plus.
I was looking at the other side of it.
Oh, yeah. Like you started it here and went down like that? Yes, but then we don't really know how long it is. Okay, we could give that equation though, and it would model it correctly. Abby?
Did you start it at 0 too? And like go up and down and back to the...
So if we started at 0, you can absolutely start it at 0, but in that case, it would be a sine curve. Because the sine curve always starts on the midline, whereas the cosine curve always starts above or below the midline. So absolutely, that green one could be a correct equation. On tonight's homework, I think we want you to do them all with cosine. In the future, I don't think it really matters which one you do, as long as you do it right. Yeah, honey.
Would the equation be -2 cosine and then parentheses theta plus pi 2?
Yes, it would be. Good job. All right, so that would be for the yellow highlighted one. Anybody want to get, Abby, do you want to give a shot at the green one? I'll give you a hint, it's easier than the one that Andi just did.
Is it just, like 2 cosine, or no, 2 sine,
Uh-huh.
and then,
Yeah,
just that.
that's it. So sometimes the sine one is actually easier than the cosine one. Yeah.
Wait, for the cosine one, wouldn't it be like a -1 at the end?
Let's see, the midline. Well, we went up to 2, and we went down to 2, so the middle of that is 0. So if you're not sure about the midline, always look at the max and the min, and then find what's in the middle of those. Yeah.
On the test, will you be restricted to only giving the cosine or the sine equation, or just whatever's easiest?
I usually leave it open to whatever is easiest. So I usually have to have like a couple different versions of an equation, in my answer key. All right, so let's talk about applications. You kind of heard this concept of the moon cycles being sinusoidal. So essentially anything that oscillates between a high value and a low value, and then back to a high value, and then back to a low value, and then back to a high value, can be modeled sinusoidally. Sinusoidally, that's this word right here. So both sine and cosine are sinusoidal curves. Tides, like in the ocean, tides oscillate between high tide, then low tide, then back to high tide, then back to low tide, and they're very predictable. The amount of time it takes to go from high tide to low tide is predictable. I have a calendar. I want to show it to you. I can't find it at the moment. I got it in Hawaii, and it shows all of the tides in a visual way, and you can clearly see this pattern of a sinusoidal curve. Now, the fact that the tides do that is because of the moon. So the fact that the moon follows this pattern and the tides follow this pattern is not a coincidence. Can you think of anything else in the natural world that oscillates between high and low value? The sun. Like, do you mean like how much sunshine we have? Like,
Yeah,
like sunrise to sunset to, yeah, totally. So it's like how long, it takes to make one rotation on our axis. Absolutely. And that takes a predictable amount of time. How long does it take? 24 hours, right? And it just repeats itself over and over and over. I saw another hand. Yeah.
You could say any type of light wave. That would make sense because they use the same type of thing.
Yeah, any light wave. And actually, I believe, well, sound is different. Don't get me started on the physics, but sound is actually a compression wave. So it's more like a slinky. But yes, light does travel like that. All right, so anything. So now I want you to think about your tire on your car. What if you mark like a chalk, with chalk you mark a star on like the edge of your tire, and let's say we were looking at that the where the star goes as you drive. Wouldn't the star on your tire kind of, let's say you marked it at the top and you started driving, so it would start high on your tire and then it would get closer to the pavement and then it would get on the, really at the pavement, and then it would get away from the pavement, and then it would get, repeat that cycle over and over. So essentially anything that travels in a circular pattern can follow a sinusoidal curve. So here we have a Ferris wheel. Jacob and Emily are riding a Ferris wheel at a carnival. The wheel has a 16-meter diameter and turns at 3 revolutions per minute. Its lowest point is 1 meter above the ground. Assume that Jacob and Emily's height above the ground is a sinusoidal function of time, where t equals 0 represents the lowest point of the wheel and t is measured in seconds. All right, this right here is enough information for you to write an equation. It's either a sine equation or a cosine equation, for you to write an equation to model this situation. So that what you could do is you could say, after 3 minutes on the Ferris wheel, where exactly are they? Are they at the top? Are they at the bottom? Are they somewhere in between? And you'd be able to figure that out exactly. Now, this is kind of a lot of information. So here's my advice. Let's draw a picture. It's always going to make it easier. And besides, it makes it funner. All right, so we've got a Ferris wheel. And let's put all of the information in the context of the picture. So it is a 16-meter diameter. And it is 1 meter above the ground. So the ground would be, down here, and then this is a distance of 1 meter. Now, what's happening is we're getting onto the bucket, into the bucket of the Ferris wheel, and then we are rotating around the circle and changing our position over time. Let's see, they told us that it takes 3 revolutions per minute. All right, so this is 3 revolutions per minute. But it says later that let's make the sinusoidal function of time where time is measured in seconds. annoying because the information was given in minutes. So let's do a quick conversion here. This would be 3 revolutions per 60 seconds. And we can reduce, so let's go ahead and reduce that. So 1 revolution in 20 seconds. Yes, I'm like, are they puking on this Ferris wheel? Because let's think about this. This is 48 feet, roughly. 48 feet diameter. And they're going around it one time in 20 seconds. They are getting sick, right? They're like plastered to the side of the bucket. Right? So I think that's kind of funny. I'm glad you picked up on that. I was going to ask if anyone thought that was a little fast. Okay, so what I'd like to do is take this information, but let's model this as a curve. Now, if it's sinusoidal, we need to figure out, is it sine or cosine? Well, where are we starting? Right here. And then what's happening? So we're starting at our minimum height. We're going up to our maximum height and back to our minimum height. So which curve can go from its minimum back to its maximum and then back to its minimum? Cosine. All right, so let's now draw like just a really rough curve with all the information that we have. So XY axis here, this is time, and this would be height at any particular time. Let's see. We have a low height of 1. What's our highest height? If we're up here at the very top, how high above the ground are we? Are we 16? We're actually 17, right? Because we started at 1 and then went 16. All right, so we are starting here, and we are eventually getting to a maximum and then getting back to the ground, or a meter above the ground. And we know that that is taking us 20 seconds. All right, what else could we mark on here? Well, do I have a midline? I clearly have moved off of the origin. I'm not oscillating around the origin. If my high point is 17 and my low point is 1, then this total distance is 16, which means that this halfway point would be what? Careful. It would be a distance of 8, but we're starting at 1. So it would be y equals 9. Okay, little things to think about there. All right, now I think we have everything that we need to write this equation. You can see here that we've got our amplitude. Our amplitude is 8. We've got our midline right here at 9. We've got our period length. We do need to kind of use that equation to find B. So this is what you need to do. You need to kind of map out all the information, put the information in sort of the context of a curve. On this next slide, I do sort of walk you through sort of the thought process that we just went through. Sketch the path, find the vertical shift, meaning how much did you go up or down, maximum height, minimum height. Maximum height was 17 meters, minimum height was 1 meter, so your vertical displacement was actually 9. If you think about where the chair is at time 0, this tells us that the function is a flipped cosine function. We already kind of discussed that. Because it starts at the minimum, goes to the maximum, goes back to the minimum. We already figured out the amplitude from our picture, but this would be the equation you could use to do that. 17 minus 1 divided by 2 gives you your amplitude of 8. And then the last piece, this is the one that takes a little bit of work. We do know that a full rotation takes 20 seconds. So 20 seconds is the p-value. We're going to set that equal to 2 pi over b, because it's the b that we need for the equation. So now let's maybe cross multiply. 2 pi equals 20b. Divide by the 20. And we're going to get pi over 10 is equal to B. That is a little weird. You will find that in these particular situations, your B value is not just like a 2 or a 4. It may very well have pi in it. So I think we can write our equation. Our height at any time t would be, our amplitude was 8, but this was flipped. So -8. We know that it's a cosine curve. The B value is pi over 10. So we've got pi over 10 times theta, or t. I should probably use t. Plus the midline, which was 9. So with this equation, I could say to you, hey, after they've been spinning around this like wheel of death for 48 seconds, where exactly are they? And you would know, oh, they're like right here. Okay. So there you go. All right, so have fun with that. Do give those word problems a try, and have a long weekend of time to do that.